semester. So this seminar series is part of our Office of Naval Research funded project, Littoral Mudflats and Shorelines, Soil, Sea, Ice, Air, and Benthic Life Interactions. In this project, we are looking to develop a fundamental and comprehensive understanding of the geomechanics of littoral mudflats and shorelines towards reliable prediction of geomorphodynamics, trafficability, and navigation from satellite images and geoacoustics surveying. So in the seminar series, we typically have guests talking either about their previous research on tidal flats or different topics, or even sometimes ideas that they want to share here with this research community. Today we have Dr. Julie Paprocki joining us. She's actually one of the team members on the project, so we're very excited to have her present today. She has received her bachelor's degree from the University of Cincinnati in 2017, and her master's degree and PhD from Virginia Tech, all in civil engineering, in 2018 and 2022. Julie started looking more at the prediction of trafficability of sandy beaches from satellite images, and then in the later time of her PhD, started looking more at muddy sediments, where she also works, or what she works on in this project with us. So we're really excited to hear from her today about geotechnical characterization of estuarine tidal flat sediments. Over to you, Julie.
Right, cool. Can everybody hear me? I'm assuming yes.
Yes, we
Okay,
can.
so today I'm going to kind of go over first a little bit about the background of why we're doing this type of work. Then I'm going to get into a little bit about what we've been doing for the last few years, and then what we're sort of working towards at this moment. So why do we study tidal flats? They're, in general, we think of them as pretty poorly understood depositional coastal ecosystems. When we think about other coastal ecosystems like sandy beaches, or even if we think about the idea of salt marshes, they're actually pretty well studied from the context of like the ecosystem service and that kind of perspective, but we don't really know a whole lot about the idea of tidal flats as a whole. They're also pretty much of a lot of interest in the military. I'll talk more about that on the next slide after this one. But they're also important critical coastal habitats for a lot of different communities. They can serve as food sources for a lot of different types of birds and different types of oysters. They're also known as to be carbon sinks, so they hold a whole host of carbon potential. They also serve a lot of flooding protection. They're of a lot of importance to the oysters and clamming community because these are the environments that a lot of those types of folks actually actively work in to be able to farm and harvest oysters and clams. They're important to indigenous communities for a lot of the same reasons that I mentioned before. They also can be found as a lot of sources of sediments for different types of salt marshes. And then finally, I always like to say this one, I find them to be just kind of fun and cool. There's something very oddly satisfying about shoving your hand into a mudflat and digging soil samples out. Okay, so when we talk about them being of importance to military operations, we're mostly interested in them from the perspective of soil trafficability, or trying to understand, can a vehicle move on this soil surface or not? When we talk about trafficability, it's primarily related to the traction, so the ability of the vehicle to actually get started, and also related to the sinkage or the bearing capacity of the soil. Now, for sands, we mostly found that it's more related to things like sinkage, where if your vehicle actually sinks too deep into the too deep into the sand, you actually then have a bearing capacity failure. Your wheel gets embedded into the soil, and it becomes challenging to get yourself out of it. And a lot of these immobilizations can be significantly challenging, and they can pose a lot of safety concerns. And when we talk about vehicle trafficability, this is of importance not only to the military, but also potentially to disaster response personnel. If you have a lot of debris on the ground, for example, and you try to drive on top of a surface, you could also get trapped into there. And so one of the whole overall impetus of not just this particular project that we had funded now, but of a lot of the work that I've been doing, and I know Nina's been doing for a long time, is to be able to develop frameworks to be able to predict the safest path to be able to traverse across not just the beach, but also now we're looking more into mudflats. So when we talk about trafficability, there is a metric that we typically use. I'll talk about more I'll talk more about that on the next slide after this one. But in general, we sort of group soils into 4 different categories, groups 1 through 4. Now, I'm not going to go over these in a lot of detail on this presentation today, but the thing that I want to point out here is that tidal flats can cover a lot of different soil types, basically everything from very fine-grained muddy soils and highly organic soils all the way up to soils that have a lot of sand but with a lot of fines mixed into it. So there's a lot of different soil classes and descriptions that can fall under this broad umbrella. And we need to be able to come up with a better way than just saying these giant broad umbrella categories, because they don't necessarily encapture all the different types of soil behavior and properties that could possibly occur. Oops. Oh no. So when we talk about assessing trafficability, we've used traditionally what was used is this tool called the cone penetrometer, which I have shown here on the screen. What this is it's a 60-degree right cone that we push into the ground at a fixed rate, and then we read the number off of the dial gauge there, and that number is in PSI. And we use that to be able to compare to those different categories that I showed on the previous slides to be able to predict what is going to be how trafficable our soil is. And so this has a lot of advantages in that it is well documented. There's a lot of standardized procedures. It's ridiculously lightweight, and it has a lot of documented use in the coastal environments. However, on the downside, this tool has a lot of limited collection conditions in that we found that on the beach, for example, when it was very humid out, that dial gauge would cloud up and then we couldn't read it. We also seemed to appear that there seemed to be a lot of operator dependence on the results that we would obtain. And we also found that there was a lot of insensitivity, even though we could like physically observe that there were differences going on at the beach. And it also becomes pretty impractical to push this thing around a whole lot whenever you have a lot of different spatial variability or you need to cover a large area. So in this overall sort of umbrella presentation that I'm going to talk about today is that we're trying to look at what sort of modern tools and technologies can we leverage to be able to characterize coastal soils more efficiently and rapidly for trafficability. So I just quickly, before I get into the nuts and bolts on this, I just want to give a quick overview. I know that there is a general audience here today, but for a lot of folks have been following this work for a long time, and I just wanted to go over what have we done so far and sort of where are we going and sort of the high level overview. So I always like to say this started before I started grad school in fall of 2016. Nina's group worked on looking at leveraging different satellite and UAV type data to be able to build mounds and pits into the soil to be able to estimate what friction angles were of sandy soils. Then I came along and started working a lot with optical data for sandy soils and looking at estimating moisture contents, where we got ridiculously good agreements between our measured moisture content and our estimated moisture content, not only for your typical quartz sand beach, but for sites with a lot heavier of mineral material up in Alaska. Then the next like 4 or 5 years of my life kind of came around, and we worked on looking at not only how do we measure the moisture content using satellite remote sensing, using radar-based systems, but we also looked at how do we estimate the bearing capacity of our soils of sand beaches. And so the bearing capacity of our sand beaches led us to develop a framework to be able to predict where it's safe and unsafe to drive onto the beach. And then we also have a moisture content study that we're currently secretly really hoping gets published here in the very near future. We looked at a whole host of different models to use radar-based data to estimate moisture content at sand beaches. So we also, in sort of parallel, but sort of towards the later years of this study, currently we're now looking more into some of the characteristics of sand beaches, where we're looking at estimating things like surface roughness values to be able to feed those into our moisture content values to improve some of our moisture content estimating. So then, as we keep going now into the fine-grained soils, we started looking at estimating moisture content with optical data, and we actually found to have a pretty reasonable match with what we anticipated to see as our moisture or in terms of what our estimated moisture contents were. The fun fact about that one was it was actually an inland study at a farm in Virginia. Then sort of during the summer of 2020, we had originally planned a very large field scale study to look more into using remote sensing for characterizing these fine grain sites. However, COVID kind of destroyed all those plans, so we sort of switched gears. And we ended up looking a lot more at the physical ground characteristics of these tidal flats to some very interesting results. Then we also spent some time the following summer looking at 3 different sites and comparing, do we see physical differences in their ground characteristics, but how do we look at their remote sensing characteristics as well? Then we sort of expanded that out and not just looked at high resolution data, we looked at a different data source to be able to look at, can we look at satellite remote sensing data over multiple years and multiple seasons? And that kind of leads us into the work that we're doing today. And so I'm going to mostly focus on everything we've done since summer of 2020 onward to sort of today, but a lot of that's still sort of in progress. So when I talk about most of our data and our studies that in this presentation today will be in the seacoast of New Hampshire, located on the Great Bay Estuary, which the Great Bay Estuary is conveniently located about 15 minutes from UNH's campus. So that makes all of our fieldwork and data collection a lot easier, especially when we think about the fact that we're interested in seasonal effects on these tidal flats, because even if it snows, I'm only 15 minutes from our different sites. And there'll be 3 sites that I'll talk about today, and I'll go through them as they come up. They're going to be called Adams Point, Woody, and Mass Cove. And so why is the Gulf of Maine, or why is the Great Bay interesting? Well, we're connected to the Gulf of Maine through the Piscataqua River. And so we have a tidal range of a little over 2 meters. But not only do we have a good tidal range of 2 meters, but we also see some fluctuation in terms of what our high tides or in terms of what our low tides are. So I was just looking at some data today, and we can have low tides with the water level as low as about 1 foot, but then we can go minus 1 foot. So we also have a pretty good range of like low tide values and high tide values. And due to the tidal range that we have here, about 50% of the whole water within the Great Bay leaves every tidal cycle. So we have quite a number of tidal flats that surround the Great Bay. And then there's also a lot of degraded marsh. So our sediments tend to be pretty highly organic. And then we also have pretty good tidal currents that are chugging through the system as well. So in our first set of studies, we were looking at characterizing our tidal flats using in situ geotechnical measurements. And this was primarily motivated by the fact that there is very limited information on these tidal flats in terms of their geotechnical characteristics. So what we did was we collected these cute little 10-centimeter tall soil samples to run consolidation and vein shear tests on them. We also used our freefall penetrometer to be able to measure those undrained shear strengths and those consolidation characteristics. And we also used a handheld vein shear data or vein shear during this experiment, but I'm not going to talk about that data today. So just quickly going over what these laboratory tests are. A vein shear test is essentially the most effective and common test to use on very soft marine soils. So we essentially shove this bladed device into the soil sample. We then crank a spring up that's attached to the top of that vein at a fixed rate. And then basically as that spring is loaded, it'll eventually fail because there's no more resistance holding against it in terms of the soil strength. And then we can use hook slot to be able to then tell us what is going to be the shear strength of these soils. Consolidation testing gives us a measure on how much the soil is going to settle due to applied loads. And so what we do is we load these samples up to a fixed loading schedule. About every 24 hours, we add in a new weight and then observe how much does it settle over that 24 hours. And we also record how much it settles over fixed time increments. And so what we're able to get out of that is not only how much is it going to settle, but we're also able to estimate how fast is it going to settle, because both of those are actually pretty important for understanding very soft soils. The other thing that we did was our freefall penetrometer. And so what this does is I have my friend Casey here dropping it onto the beach. And so as it falls through the air, it'll eventually hit the soil surface. As it hits the soil surface, it'll eventually come to a stop. And then we can record the deceleration as it comes to that stop. We can also measure pore pressures through a pore pressure element that's attached to it. And then using our calculations for sediment resistance force, which we can get using our Newton's laws of motion, we can also we can obtain what our penetration depths are by integrating with respect to time, and then calculate a dynamic bearing capacity by dividing that sediment resistance force by the cross-sectional area that's in contact with the soil. So we can use different correction factors to be able to convert that dynamic bearing capacity into a static bearing capacity. I have one shown here for demonstration purposes here today that we call the logarithmic approach. But just note that there's a lot of different values of this out there in the literature, but this is the particular one that we applied for this study. And then we can also use this penetrometer and these dynamic and quasi-static bearing capacities to be able to estimate our undrained shear strengths. And we can use our pore pressure measurements to estimate our consolidation parameters. So this is just what a standard deceleration profile looks like. We can see that we have our depth calculated, we have our measured deceleration, and then our velocity that we calculated from that deceleration profile. And then we also then have our quasi-static bearing capacity shown here on the right. And we have this calculated for three different, or we have the dynamic one that's shown here as pink, which I'm going to call K is equal to 0 because there's no correction applied to it. And then we increase our K value, which is used to correct our dynamic bearing capacities into static values. We can see that increasing as we move to the left. So to be able to calculate our consolidation parameters, what we do is we can let this penetrometer rest in the soil for a fixed amount of time, usually somewhere between 30 minutes and an hour we found to be pretty good. And what we do is that we monitor the pore pressures from the time that the penetrometer inserts itself into the soil until we pull it out. And so what this allows us to do is this allows us to observe how our pore pressures dissipate with respect to time. And so we can use a method that was developed for cone penetrometers. For those of you that aren't familiar with cone penetrometers, those are essentially the gold standard for characterizing soils. We can use a interpretation technique that was developed for cone penetrometers and then validated by another student of Nina's, Bilal Montaz, to be able to then calculate what are some of the important parameters. And in our case, we're calculating what is the rate of pore pressure dissipation with respect to time. So the site that we did this at was what we call Adams Point. This is located on the Great Bay Estuary near the Jackson Estuarine Lab, which is a UNH-owned facility. So this gives us very easy access and a lot of resources that allow us to leave out equipment for longer periods of time. We found that this site had about 89% fines with about 11% coarse-grained materials. The soils using our Atterberg limit classification following the unified soil classification system. We had a liquid limits between 39 and 49, and then plastic limits of 27 to 35. If you're not as familiar with what that means, those are basically just metrics we use to monitor how much water is in the soil between when it acts like a liquid and when it acts like a plastic. So those numbers represent percentages of moisture. We just don't ever present them as percentages. Our soil classification was an ML, or a low plasticity silt. We had in situ water contents ranging somewhere between 64.7% and 86.6%, and then average dry unit weights on the range of 8.3 kilonewtons per cubic meter. So this is just showing you all of our penetrometer data that we collected. We collected data over, I believe it was 3 different transects. And what was really awesome to us, it was actually like pretty stable across the entire flat. So we were able to get pretty consistent measurements over the entirety of the area that we were testing. So then what we do to be able to convert our dynamic or our quasi-static bearing capacity into an undrained shear strength, which is that really important metric for quantifying the strength of really soft sediments, we divide by this cone factor and KT. And so in this study, what we did was we ranged that cone factor between 10 and 12, because that's sort of the standard value that's been used across a lot of different very soft, normally consolidated soils. And we also tried out 2 strain rate correction factors because some of the work that some of Anina's other students had been doing had demonstrated that we potentially didn't actually need to potentially need to strain rate correct any of our data for this. And so we wanted to test that out because one of the main benefits that this study allowed us to do that not a lot of our other penetrometer studies have allowed us to do is that we could collect very carefully collected samples because we were sitting on an exposed tidal flat and didn't have to worry about pulling samples back up through the water. So we used our vein shear testing, compared that to our calculated values of undrained shear strength from the penetrometer. And I know it doesn't quite look like it's perfect agreement, but we actually had pretty good agreement, which was super impressive to us. We do suspect that some of the issues that we had was due to the fact that there's a lot of shells and gravel fragments within this tidal flat. Specifically, there are oysters and different snails that live in this tidal flat. So as we insert that vein into it, we could be hitting some of those oyster shells or those snail shells as we're doing that testing. So the other thing that we did was we then calculated what our coefficient of horizontal consolidation would be for our dissipated pore pressures. And then we used a calculation from this paper in the 90s to be able to determine what our coefficient of horizontal consolidation was. And basically, because what we're actually interested in is going to be our vertical consolidation, because the horizontal one is assuming that water leaves out horizontally through the soil layer. Most times we don't really care about that. We mostly care about vertical movement of water through our soil layer. So we can use a relationship about our permeabilities to be able to calculate what that vertical value was. Now, this next part actually makes me super happy because a reviewer actually suggested that we try this particular analysis out that I have shown here from Bailey and Levido, and I don't know how to say that correctly, so if anybody knows, please tell me. But they suggested to use this correction, looking at this recompression ratio and this compression ratio that are based off of index properties or standard values to convert our measured value from our penetrometer to our expected value for our C sub V. And so what we found, which was super exciting to us, is that the data actually lined up super well with what our laboratory testing was. So the ones that I'm circling now are what we measured using the penetrometer and using a couple of different corrections. The first one from NAVFAC has to do with looking at what your soil properties are. And the bottom two have to do with the correction based off of looking at the penetrometer data. Everything started to align, which is super exciting that that actually managed to happen. So then the next phase of this work that we were interested in was looking at how do we use remote sensing data to characterize index properties of tidal flats that are going to be of interest to us. Now, a lot of this is motivated because there is very limited work that's actually been done on purely fine-grained soils. Some of the existing work that's been done out of the Netherlands and South Korea back in the early 2000s was mostly focused on more sandy flats, whereas we have a lot of interest in these very muddy flats because these tend to be the most critical and like the worst types of soils for looking at trafficability. The other challenge that also arises is that a lot of studies have not looked at seasonal data. So that's still something we're still working on, but I'll present a little bit about what we've done about that so far. So a lot of these have been very like one-time surveys and not really caring about what happens to these tidal flats at different times of the year. And so what we did for this is we had some physical sampling, and then we also added on two new sites, Mass Cove and Woody. So Mass Cove is a sandy tidal flat that can be broken into two separate sections. We have a coarser section that I have shown here in the light blue, and then we have a finer zone that's shown here in the darker blue. And so the coarser region has about 84% coarse material and 16% fine material. The moisture contents range from about 17 to 41%, with an average of about 27%. And then we have a finer zone that still is actually a coarse material. It's still a sand, but it has about 69% coarse material and about 31% finer material, with generally a little bit higher of moisture contents in our coarser zone, an average of about 35%. And we found that the flat actually gets finer as you move towards the center of it. And we had a whole slew of different USCS classifications. We had silty sands, poorly graded sands, and poorly graded sands with silt. So there's just like everything at this site. And then we had much higher dry unit weights than what we were seeing at our muddy site, where those range from about 15.7 to 16.7 kilonewtons per cubic meter. So just to show some data about what this looks like, in our cross-shore data, we see actually pretty uniform. This is going to be our coarser zone. We can actually see a pretty uniform moisture content and even grain sizes across that entire region of the flat. But then as we go along our longshore, which is actually our finer zone, we can see that we have an increase in moisture content, and we generally see an increase in what our fines content is. And so looking at how those two are related, again, we generally see that as our fines content increases, our moisture content increases. Not super shocking, that is about with what we would expect to be able to see for a site like this. The other site that we also added is what we call Woody, because it is found in the woods, but it is around the corner from where Adams Point is located. What makes this site pretty unique is that there's a plethora of drainage channels that are crossing this site. You can kind of see them in this image here, but if you look at Google Earth and zoom in pretty close, it's pretty obvious. It's actually a layered fine grained material. It's a little bit hard to see from this figure I have shown on the top here, but there's like this incredibly soupy layer on top that's followed by this significantly more consolidated and denser layer at the bottom. When you poke it with your fingernail, there's like a definitive difference in how those two different layers feel. Now, most of my USCS classification data is actually on that upper layer because, again, we only use those 10-centimeter samples. Hoping to, now that I have deeper sampling from another one of the PIs on the project, we'll be able to get deeper soil samples to actually characterize that lower layer. But our upper layer generally classified as an elastic silt, which is a high plasticity silt, and it has a liquid limit of a 61 and a PI of 17. Our water contents are higher than what we saw at Adams Point because of that soupy upper layer of about 84 to 190%, which is insanity. And that average dry unit weight of that upper layer is about 6 kilonewtons per cubic meter. And then one thing that I think is interesting about this site, and I'll actually skip to the next slide to demonstrate this here, is that it's actually backed by a heavily degraded marsh. So where I have my laser pointer here and where my colleague Greg is standing in the other image here, that's a marsh that's actually been rapidly decaying over the last like 10 to 15 years or so. So there's a suspicion that there's a lot of input of organic material into this tidal flat. In addition, not only is there this salt marsh where my laser pointer is here, there's this other salt marsh back in here that's also been heavily degrading. Colleague Greg that I showed on the previous slide there said that when he started at UNH, salt marsh used to be covering all of this area here. That's no longer true, as we can see from the satellite image. I think this is from like 2022 or 2023. And so this creek that we call Cromit Creek is then depositing all of these organic soils potentially onto this tidal flat, which makes it quite interesting as a comparison to our Adams Point site that does not have all of that organic material being fed onto it. So looking at what our soil properties are for this site, we can see that our fines content at Adams Point and Woody is substantially higher than our fines content at Mass Cove. And then our water contents at Woody are way higher than they even are at Adams Point, but we can still see that Mass Cove is still lower than the other sites. And then looking again at that moisture content versus fines content relationship, we can still see that increase across all three of those sites, that as our moisture content increases, our fines content also increases. And then we can also see that as our fines content and our moisture content both increase, we see a decrease in what that undrained shear strength was. So how did we actually go about using remote sensing to be able to characterize them? What we used was what we call synthetic aperture radar, or SAR. And these are images that are composed of the intensity of radiation that is backscattered from the ground surface. So as the satellite flies over the over our site of interest, it shoots down a radar signal. That radar signal will hit the ground. Some of it will be absorbed by the ground, some of it will be scattered away, and some of it will return back to the satellite. And so we use what's returned back to the satellite to characterize our sites. And so for bare soils, we look at this as being a function of both our satellite characteristics and our ground properties. And our ground properties of interest are mostly related to the water content of the site and then the surface roughness of the site. Now, one thing I would like to point out here is that we look at these radar images as being what we call our backscatter coefficient, which is just a log transformed signal power using units of decibels, because backscatter can span so many different orders of magnitude that if I kept this in the raw scale, we wouldn't be able to see anything. So when we talk about our surface properties of interest, we're interested in two, like I said. First is our surface roughness, which is going to be our variation away from some sort of mean reference surface. Now, this can either be a flat surface, a periodic surface, or a slope surface, and we use a property called the RMS height, or the root mean square of surface roughness. The second thing that we look at is our water content, which we do that by proxy of our dielectric constant. And this is just a quantity that is able to measure the electric potential within a surface, basically. And so the reason why we can do this is that air has a dielectric constant of 1, water has a dielectric constant of 80. Dry soil is somewhere between like 4 and 8, depending on the type of material you're looking at. But we can see that as our soil gets wetter, what's going to happen is that our properties of the air can't change, our properties of the dry soil particles can't change, but the amount of water within that that matrix can change, so that will change the dielectric constant of the overall mixture. So looking at how does our fines content and things like our median grain size, both of these are known to be critical for characterizing our sandy flats. How are those related? Well, as our backscatter increases, our fines content generally has been shown to decrease. Seems a little bit counterintuitive, but a less negative number is a bigger number, so keep that in mind there. But as our median grain size starts to increase, that's when we start to see what our backscatter coefficients start to increase as well. So looking at a lot of different data, what we wanted to also do was look at how are the different properties across these different flats changing with respect to our backscatter signals. So what we did was we looked at extracting out our entire tidal flat out of our images and then plotting all of the different backscatter coefficients that are going to occur for that different tidal flat. And so we collected 9 images in our 2020 and our 2021 surveys. We've actually collected quite a few more since then, but I'm just showing the few selections that we have here. And then we collected them at a range of different incidence angles, so a range of different parameters for data collection of all of our different sites. And so what we can do is we can characterize those histograms by using these different statistical measures of texture. We have 6 of them here. I'm going to focus on the mean and the entropy. I'm going to cross out those middle 2 because they actually end up not being super applicable to our tidal flats at all, mostly because of the way that we have to normalize our data. And so our mean value is just that. It's the average value of that histogram value, or the values of backscatter within that histogram. And then entropy is just a measure of randomness of the values within that histogram. And so when we go ahead and we plot our values of our mean backscatter for all of our different images for our different sites, we can see some unique trends that are starting to develop. So for example, the coarser zone of Masco exhibits much higher backscatter values, which is not shocking because those should have much lower moisture content. So because they have much lower moisture content, as we saw before, lower moisture content means higher backscatter values. But we also know that for the much wetter surfaces, we see much lower backscatter values. That's very hard to always keep track in my head, so I apologize if I say those backwards. We also look to see if we see them over a whole range of incidence angles. We actually saw pretty consistent trends. Generally, we always saw the lowest backscatter values for that woody site, and we generally always saw the highest backscatter values for that mass cove site. Looking at what our entropy is, I'm actually going to go ahead and cross out my mass cove coarser zone because we already established what an expected trend is for to differentiate that because it's coarser away from our finer sites. We can see 3 very unique trends start to develop where we have the highest values of entropy for woody, which we suspect is related to not just the surface property itself, but also might be indicative of those different tidal creeks across the site. We see the lowest values for that finer zone of Mass Cove, which also somewhat makes sense because there's less less roughness and there's also less tidal creeks across it. Whereas at Adams Point, we see these like very distinctive pillow hollow structures. So it makes sense that that would fall into the middle section there. So then when we look at developing what this classification might look like, we can then draw a boundary between what our mean backscatter is for our coarser zone and then our finer zones. And then we can draw tentative boundaries for our entropy to determine between our 3 different sites. So this is good and all, super exciting, but this only represents, I say 1, but it's really 2 snapshots in time. I say 1 because they're both for the summer months, but it was really over 2 years. But what happens the rest of the year in a place like New Hampshire? It gets very cold here during the wintertime. And so we tend to see ice formation, and we can also have differences in biological activity throughout the year because not all things thrive in cold weather. We can also see different sorts of algal blooms or different sorts of critters that are forming throughout the year. And then what happens over many years? As I said, we have a lot of degrading salt marsh in our area. So we have a lot of different organic inputs that have been put in over the last 10, 15 years. So is that changing things like our backscatter signal? So what we turned to was the work. This is actually the work of a master's student of mine, Tess Priest. She graduated last year, where she was looking at using publicly available synthetic aperture radar data to be able to see, are we able to use this to look at different soil properties over multiple years? And so what we turned to was the C-band Sentinel-1 data, which is a free open source data source that anybody can access. And so one benefit to it is that it actually comes with two separate polarizations. So it comes with two different types of data for I say the price of one, but it's free, so who cares? But we have our VH polarization and our VV polarization. And so what she did was she spent a whole lot of time going back through the record. She went from, I believe, 2020 onward to end of 2023. And she looked at when do we anticipate having low tides? And then when we do anticipate having low tides within those satellite data, we were able to then pull out what are going to be the backscatter coefficients for our different tidal flats. And so what we have shown here is our VH polarization histograms of backscatter. You can see that there's not a ton of trend that's happening here, but when we switch over to our VV polarization, we are starting to see trends that are developing. So what we did was we looked at what are our mean backscatter for both of those different polarizations. One thing that's notable to point out here is that our VH polarization does not have a ton of trend that is going on. But when we look at our VV data, we can see that our Woody site is consistently having, again, the lowest backscatter. Adams Point is somewhat in the middle. And then our Mass Cove site is actually, again, going to have the highest backscatter return. So then what she did was we broke it down looking at what all of our different mean backscatter versus our entropy, much like we did in that earlier study. Except now, one thing I want to point out that we did slightly differently is that we broke it up by orbit because we actually have 3 different satellite passes that come over the Great Bay. And then we looked at, okay, what do these trends in backscatter look like over these different orbits and for our mean backscatter and our entropy. And so one thing that's interesting is it doesn't separate out as cleanly as we did for that earlier data set. So what we ended up doing was we ended up looking at our Mass Cove site combined as one whole region, because we suspect that due to the resolution of the C-band data, we actually don't have the ability to be able to capture those fine spatial changes. Our earlier X-band data has a image resolution of about 50 centimeters per pixel. This has a resolution of about 10 meters per pixel. So that leads us to the suspicion that we're not going to have great matches that are going to happen at all times to determine those finer zone and that coarser zone only because of that image resolution. So what we ended up doing was looking at using a decision tree to develop these different boundaries for our 3 different orbits and then all of our data combined together. And we actually found a pretty good match, which was really incredibly exciting for us to be able to separate these out into different categories. One of the things that we suspect is that there are some areas due to ice formation, wind, and rainfall that are going to be impacting the surface. Using some optical data for some context clues, we do believe that there was some ice formation over the time period that we were analyzing. So that could have a pretty significant influence in terms of what our backscatter coefficient is. The other issue that we have, which I'll actually get into a little bit in a few slides, is that we do suspect there's some inaccuracies due to the timing of the tidal cycle and the drying time. So as a tidal flat if we are to image a tidal flat right as it goes to low tide, we're going to, in general, have some sort of differences in our properties that if we were going to image as the water was coming in, only because there's times that's going to then allow the tidal flat to dry out, as opposed to just being completely saturated. The other issue that we might also have is that we are using a predicted water level. We don't actually have measured water levels for these sites. So we suspect that there might actually be some issues with us just selecting a random water level as our quote unquote low tide marker. And so there might also be issues of us actually selecting the proper area of our tidal flat. So where are we headed to next? So we have a few things that we're actively working on right now. The first is going to be the segmentation of SAR images. So how do we break our different SAR images into different areas? So this is just a pretty rudimentary one that we have shown here, where we have broken it into vegetation, water, and urban area. which give us actually pretty decent results, but we're looking at, can we put this into more classes than just these 3 individual classes? Why is this important? Well, if we're able to then break this into different, if we're able to segment these images into different regions, then we're able to identify, for example, where is exposed mud, where is land, so that we can better understand the coastline towards being able to pull out where is the trafficable areas of these images. The other part that we're interested in, and I've been talking a lot to some folks over at UMass about, is they work a lot with oystering communities. And so they're interested in seeing what sort of metrics can we relate to our different soil properties, so that they'll be willing to give us data and don't have to haul around different equipment or collect soil samples for us. So they're interested in understanding how much can we relate how much we sink into the mud flat as we walk across it to different soil information. So I just have it for our 3 sites shown here, where generally, as we see our fines content increasing, we can see an increase in terms of our penetration. As our dry density starts to decrease, we start to see as our dry density starts to increase, we see a decrease in our penetration depth. And then same thing with our moist density, is that as our moist density starts to increase, our penetration depth also starts to decrease. Other properties that are also of interest could be things such as organic content, or looking at also water contents as well. Other things that are of interest, particularly for that woody site, is how are our different soil properties changing with respect to depth? As I mentioned before, most of our sampling has occurred within 10-centimeter samples, but recently we've started digging quite literally a little deeper into the mudflat using a soil corer. It's pretty basic, so we have a pretty tough time doing it. Again, I'm hoping that Emily's soil sampler that I have now will help us fix some of these problems, but we're interested in seeing how do these properties change with depth. So right now I just have shown here what our loss on ignition for our organic matter is. We can actually see it's fairly consistent with depth, but we suspect that our upper couple centimeters is actually going to have quite a bit of difference. We're currently working on how do we properly sample that as well. And then we can also see that as we go with depth into both those Adam Point and that woody tidal flat, we're seeing a decrease in what our moisture content is. And something like that might actually end up being quite critical for trafficability, because even though we might have a really soupy upper layer, maybe we actually have a really dense lower layer that even if that soupy layer isn't going to support us, maybe that denser layer will. And clues such as moisture content or organic contents may be important towards understanding that. Next is also looking at the roughness characteristics of tidal flats. I only really have a couple shown here, and I should also say it's not just really roughness, but it's different surface features that are happening. For example, this image that I've shown here with this pink coloring on there, we suspect that we're really not sure what was going on that day. It was just super cool, and we were all just geeking out about it and collected some samples. But we suspect there was some sort of algal bloom or some sort of like material that had got deposited onto there. And it's interesting to think about how does that change our remote sensing signals. And then for a lot of our sites, particularly these muddy sites, we see a lot of these pillow hollow structures where water actually ponds in there. And is something like that going to be important towards understanding what the soil properties are? And then finally, as I mentioned before, a lot of times right now, we're just assuming a water level to tell us, oh, it's low tide. That's great. We have this much mud flat exposed. But we know that's not exactly the greatest picture of this, especially again, for a site like up here where we have a pretty good tidal range that's going on. I pulled some data for our water levels at our site. This is again, a predicted value for the next week. Yeah, about a week, 2 weeks from now. And we can see that we have over even just this 5-day period, we have a low tides ranging from 0.37 feet all the way down to negative 0.71 feet. So that's already a foot in and of itself will change how much of our tidal flat is exposed. And then we also have low water levels that are actually much higher than that on the range of about a foot to like 1.3 feet. So we can easily see that we have quite a bit of a range going on here. And so we need to better understand where is our actual tidal flat located. So we are working on ways to be able to address that. So this is just a whole bunch of papers and references for this. But just want to say thank you all for listening, and particularly thanks to the Office of Naval Research. I was trying to count this up yesterday, and I think what I talked about today is the summation of about 6 different research grants, including the three, well, the one of them just ended, but two that are currently ongoing. So this has been a very long game and a lot of different projects and work that has gone into this. Two former graduate students at Virginia Tech, and then Freddie, who's shown here, and then a whole slew of my research team here at UNH, including some undergraduate students and graduate students, as well as Gabe Venegas and Tom Littman, who are both professors here, who have done a ton of work for helping us with this type of project, and then their research team as well. And then finally, the folks at Sea Stars and then Nina, because she kind of started all of this. But you can see some pictures here that I think are fun to think about. Some of the surveys that we did, particularly for Freddie's work, we had to do them in the dark on the Great Bay in December, which is very cold, and we were wearing headlamps to be able to collect this data, which I think is kind of hilarious to think about. So thanks for listening, and I'm happy to take any questions that you guys might have.
Great. Thank you, Julie. Fantastic talk. And we do have already a number of questions
Oh
in the
boy.
chat. And I will just start practically how they appeared. So the first
Okay.
question, actually the first three questions came from Reggie, and I start with the first. So why the penetrometer has 5 vertical accelerometers? Is that for redundancy or are they noisy?
Yes. So as far as I understand, it is for a mix between redundancy and it's also because we have different ones, and I did not mention this today, but we have different ones that are sensitive to different levels of deceleration. So the lowest one should be for 2G of deceleration, then it's 1850, 200 and 250. I think I said that all right. And the reason why we have multiple is that sometimes at these, sometimes those higher ones have a lot more noise in the signals. So we don't necessarily want to use the highest one always for these really soft soils.
Great, thank you. And then the next one from Reggie is, when you say mean backscatter, what physical area is that
Ooh.
from? 50 square meters, 100, more?
I will have to get back to you on that because I do not have those numbers off the top of my head. I do know they're in they're in, I think, all of the papers though, but I'm happy to follow up about that one. Our sites are really unique in that they're actually like pretty tiny tidal flats. Well, one of them is pretty tiny, one of them is much bigger, and then the Mass Cove one is sort of in the middle, but I do not remember the exact values off the top of my head. Yeah.
Okay, great, thanks. And then have you tried other modalities like soil or mud temperature or other local variables like water temperature or air temperature?
Another great question. I would also have to follow. I have not looked into those too much as well. I think Gabe Venegas, who's an acoustician, he's been using our sites as like calibration for some mud models for acoustic backscattering. And so I believe he collected some of that data, but I have not looked at that really in comparison to like the remote sensing data, but that's a really good point.
Great. Thanks, Reggie, for your questions. And then we have a question by Joey Yang. Can you elaborate on why backscatter in the VV polarization has clearer trends than the VH?
Yeah, that's another great one. So it has to do with the fact of the way in which the signals are sent and received. So basically, when the VH is sent, is that the VH is sent down in the vertical direction and then received in the horizontal direction. So generally, that means that there's going to be a different way in which the signal is sent back to the satellite. And in general, it's been observed that because of those changes in direction, there's more like depolarization of your data. So it doesn't come back as cleanly to the satellite because you're sending and receiving in a different direction. So generally, it's been found in the literature, and I guess supported by our work as well, that the VV data tends to be clearer because it's able to be better received because you're sending it and receiving it in the same direction. And it's also more sensitive to moisture content than it is if it's sent and received in different directions.
Great, thanks. And while other people maybe want to have the chance to put more questions in the chat or just raise their hands, let me actually follow up on Joey's question. So how
Yeah.
does HH fit in there?
Yeah, so actually HH should be the best. I took the slide out, but I'm actually going to just pull that up actually right now and share I guess pull my screen back up. So when I say VV, it has to do with a parallel to antenna. HH is perpendicular to antenna. So in theory, HH should be the strongest. And I would have to go back and remember why, because I do not have it off the top of my head right now. But it has to do with the way in which the signal is sent down and sent back up. So in theory, it should be VH should be the worst, VV should be in the middle, and HH should be the best. And there's a lot of different studies related to moisture content that supports that.
Okay, great. And can you remind me, most of the X bands are HH, right?
Yeah, yep. So
Yeah.
all of the X bands we've done are HH. I think we have a couple of C bands that might be VV. Some of the radar stats might be. I'd have to double check that though.
Okay, great. I don't see another question here right now yet, but I have another one. So I was intrigued by the orbits.
Yes.
I assume that's now site, the orbit numbers are obviously site specific, right? So
Yes. Yes.
can you a little bit elaborate what that actually means? Is that larger distances, different angles, and how would that relate to other sites?
Yes, great question. So I would have to I'd have to pull up the paper to remember exactly every single detail to it, or in terms of which one was which. So for the Sentinel-1 constellation, at the time that that test started looking at the data, there were two up in orbit. So there was Sentinel-1A and 1B. Well, unfortunately, and so 1B came over the Great Bay once a day or once every 12 days, and I believe that was orbit 40. Whereas 1A came over two times. One would have been an ascending orbit and one would have been a descending orbit. So basically different directions of passes that were coming over the Great Bay. I don't remember exactly which one corresponds to which. I would have to go back and look at the paper to remember how that goes. But the reason why the reason why we don't have as much data for orbit 40 is that Sentinel-1B unfortunately went down in December of 21, I want to say the date was. So it was no longer collecting data. So we only ended up having two that had data for the full time span. But actually, very recently, within the last year or so, Sentinel-1C went up. So now we're back to having two or satellites orbiting over all of the same time. So in theory, we should be able to have at least two passes over every single site, basically one from each 1A and 1B, or now I guess 1A and 1C. Basically every 6 days, I think is the timing on that. It might be every 8 days. I forget if, or sorry, every 9 days. I can't remember if it's a 12-day orbit or an 18-day orbit. So in theory, we should get two images within every 12 to 18 days. But in theory, you could have as much as four for every single site because you could have an ascending and a descending pass, which basically just means like, is the satellite starting at the North Pole headed to the South Pole, or is it starting from the South Pole headed towards the North Pole?
Hey, great. Thank you. Okay, I just saw.
Which would be actually really great for a lot of our sites because then this gives us, I mean, the X bands are great because they're very targeted, but then this just gives us just a ton more data to look at.
Okay, great. Thank you. I see here another question from Sophia. You mentioned that the SU, so under shear strength, I assume dynamic, measured from the portable freefall panotometer was close to that which was measured in the lab with the vane shear. Were you able to measure shear strength in situ using any other tools as another data point on shear strength? And then
Great. Oh, sorry, go
what
on.
yeah, what about other tools to measure unconfined compression strength using a pocket pen, for example?
Okay, so the first part of that, great question. I forgot to put that in here today. We actually bought, it's not in my office right now, but we bought a like a GeoNor testing vein that allows us to go down pretty deep. And so we do have some profiles of the undrained shear strength from that. Now, I know that's not like the perfect way to be able to test vein shear strength because it's still somewhat user dependent, but I do have that data. I just forgot to plot that here, or I did not get a chance to plot that here today. The other thing that we also have is that UNH fortunately owns a really old Context CPT. So one of the things that we're trying to figure out how to do is to be able, we actually have a setup to be able to do it manually. So we would love to be able to push our CPT into these profiles, just like hand pushing it in, kind of like the way that Naveed Jafari's group does it, but instead of it being shorter, we actually have it can be much longer than that. So hopefully someday we'll be able to do that. Right now we're in a little bit of a pickle because the Adams Point site, they're currently renovating the Estuarine lab, and one of the projects as part of that was a shoreline stabilization project. So we're kind of being told to keep away from that, which would be the perfect site to do it at because they have plugins and power generation that we could use to run a CPT. So that one's sort of on the to be determined only because we have a little bit of trouble accessing that site right now. In terms of things like pocket penetrometers, we did have this thing called the Soil Saver. I did not show it here today, which is another vein shear device that Nina has, and part of that does have a like pocket penetrometer on it, or a little penetrometer on it that I believe measures an undrained shear strength. Did not ever really do an unconfined compressive strength. I would be questionable about that with how soft these soils are. I mean, we're talking about incredibly, I'll just zoom back to that slide here. We're talking about incredibly low undrained shear strengths, like less than 5 kilopascals. So I would be questionable if that would be accurate. But we did try, one of the things we did try was to do a UU test here in 2021, because we actually have a pretty like swanky UU device here at UNH. We had a heck of a time getting a membrane around a sample though, because when we would go to roll it up, we would basically squash the whole thing because these are, again, very soft soils.
So I turned my mic on because it might just be easier for me to talk to you
Yeah.
about it. So that's kind of what I was thinking. I was thinking that maybe transporting samples back to the lab might cause some issues. So what
Yeah.
other kind of methods that you can use in the field to get some other measurements just of SU or some other soil parameters in situ to either confirm or deny what you're measuring in the lab? Because those very soft soils, as I'm sure you've experienced, don't really stay intact at all once
No.
they come out.
Which,
Um,
and we even had the problem we were doing the consolidation tests were very interesting. We eventually got a method down to do it because we could basically like put the ring on top and then pull the sample out, and then the ring would basically fall in as we were pulling it out. So even those, I'm like, everything is very much like, hey, it's all really soft. So like lab and soil testing is a pain.
for sure, for sure. I would wonder if there's a couple things that we could maybe kind of develop to deal with how soft these are that could be kind of in situ versions of those lab tests in
Yeah, and
order
I
to
I
get those
definitely
measurements directly.
I definitely agree with you. There is a lot of I always everything is I think the error bars on this are pretty beefy too, if I remember correctly. Only because, like you said, there's so much like uncertainty in what these have to be because of how soft they are. But I definitely agree there's ways I think to replicate some of these tests, which is why like I would be interested in seeing can we push a CPT into these sites just because we know so much more about how to interpret that data than we do with the free fall penetrometer data that it would be like the gold standard comparison.
Yeah.
Yeah. And I think so you may want to think about that if you're how much power your cone needs. So I mean
Right.
we can carry like one of the lithium battery packs on the hovercraft, right? And we can
Right.
also probably carry that cone on the hovercraft. And so then we could actually have everything on that. I mean, probably there's not much more on the hovercraft then, but I think that it could carry it with two operators or so.
Oh yeah, and Jean Benoit, and this was something I've always thought about, was Jean Benoit had built like a manual push system that I inherited it. I don't know how to run it at this point in time. It's been a slow burn to get that stuff running. But I also always wondered if that I think is overkill for these sites, but he definitely has thought about ways, and we've talked about maybe are there ways to push this in from things like the hovercraft or from like one of the small boats that even UNH has could be potentially useful.
Yeah, yeah, we can certainly try that. And then the new penetrometer with the commercial cone that we developed under the DURIP, that in
Yeah.
the lightest version should also be able to go on a small boat, and that actually just here in the St. John's River did like 3 meters of penetration depth.
Oh,
So that
nice.
would be another option that we could look into. So very
I
cool.
will say we're also like pretty fortunate that Vertec, or sorry, we have a Vertec cone, I apologize. Vertec is also located very close to us, and I know a lot of the folks up there now, so I've been chatting with them a little bit about
Great.
their thoughts on this.
Awesome. Okay, last chance for the audience for our last question for the first, second, third. Okay, so then thanks everyone for attending. I'm sure you can find Julie online. She's an assistant professor at UNH, so just look her up if you have following questions, and I'm sure she's happy to answer them via email or meet with you. Again, thanks everyone for attending. We are probably looking at our next seminar in 6 to 8 weeks. So stay tuned for announcements for our next presentation. And thanks again, Julie, for a fantastic presentation with like really your whole sequence of this work that you have done and also an outlook into the future. Thank you very much. And thanks everyone for attending. See you in a couple of weeks.
For listening,
Bye-bye.
everyone.
All right. Good job, Julie. Bye.
Yes, Sophia, I could if everyone's okay with us staying on for a second to chat quickly, it'd be great.
Oh, yeah.
Hi, Julie.
Hey.
I'm officially here at University of Florida, so I've had some time to put my head on and start really
Yep.
thinking